Hi, and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. So, a lot of stuff going on during this episode. Let me show you. Alright, so we are doing cleanup and better metrics. In the previous episode, we used big primes optimizations to get our 200-bit execution performance to just 126 seconds. And while our performance soars up, our code becomes more and more messy. So now it's about time to switch into a more reasonable representation of it. Prepare yourself for a massive cleanup. But that's not all. There are some metrics optimizations as well. We don't need to make a recursive call as we did in episode 8. It only adds noise. The algorithm works without it as well. Let me show you that part. In episode 8, yeah. So the algorithm will save bsmooth into bsmooth list, add new row to the solution matrix. For each bit index in the bsmooth vector, check an eliminations map if we have eliminator that can eliminate that bit. Now, what does that portion remind you? It's exactly the same thing that we are doing today with the big primes. We are searching to eliminate the big prime and convert it into a bsmooth value. And we don't do a recursive. Now, let me continue for a bit longer. So we have this eliminations map of eliminators. Now the bitmount is either a solution or an eliminator. And then we are adding it to the eliminations map by finding the first index of one bit of the eliminators vector, or we extracting a solution out of it. And for each bsmooth in the bsmooth list, check if it has the eliminator index. And then we recursively call to that entire thing all over again. So that part is not needed, because just like with the big prime optimizations, we can simply use this map and that's all. We do need to maintain a solution matrix to extract solutions, but we don't need a recursive call. So the entire algorithm is actually improved from O of n power 3 to O of n power 2 for each addition of new bsmooth value. Okay. So that one is big. Next, during solution execution, we almost ran out of memory. I was actually waiting for it to come up with this optimization. I was waiting for us to get out of memory exception, but it didn't happen. It happens for some much bigger values of 250 plus bits, and those takes very long time to execute. So we didn't get into that yet, but I do want to perform the out of memory optimization now. So during solution extraction, we almost run out of memory when computing BigIntegers. We can use the below observation to keep our calculation within the bounds of n square. It saves about 5 seconds of the solution extraction time and about 2 GB in memory usage. Yes, a lot. It unblocks us in targeting some really big numbers. Our goal is to calculate a power 2 minus n equals square. Now, this is a very generic representation, and let me show you that it doesn't conflict with our multiple enamel optimization, because in the multiple enamel optimization, we are looking into that relation. But in our code, once we are converting it, we are calculating B as that thing, which is similar to that. It doesn't really matter what is A. And as for A, those are different, but we're calculating this entire expression to, to, to maintain the similarity in here. So this is A before, and this is A now in our new solution. The way that we structure it in the source code. So when we are extracting the solution, we can continue and treat it as this simple form of A and B. And now behold of this optimization. AB, different A's, A and B, equal C mod N. Now that can be written as A mod N times B mod N equals C mod N. So we don't really need to compute the product of all of our relations and then do the addition and the GCD to extract the solution. We can always keep it mod n, and so in the worst case, our big integer will get as big as n power 2, but not further. And that reduces from 2 gigabytes of memory for computing those huge integers into just a few kilobytes. So this will help A calculation since we have access for A, but we don't have access for B until we multiply all of our relations and perform the square on the final result. We do have a vector of primes with an odd power, so we can write B in each of those relations as B tag V equals B, where V is the product of all the primes in the vector, and B tag equals to B divided by V. That also implies that B tag is a square, since we extracted all the primes with odd power out of it. Since we did it by removing all the odd primes. So now it must be. We can now use A optimization, that part, for beta calculation. As for we can create an array where we track the powers of all those vectors as we multiply the relations. At the end, all of the powers must be even, and we will multiply B by those primes and mod n. That might sound a little bit complex. It will get better once I show you the source code. So we will come back to it with another explanation, and I hope it will be clear then. Okay. One of the biggest things that I noticed during the cleanup is that we are working with executor that requires a new runnable creation each time we switch threads. It causes thread overhead. So now I switch to working with blocking queue that have predefined objects to pass jobs between threads. It solves the thread overhead problem and gives better performance, about 15 seconds better. The new structure is as follows. Polyminer generates polynomials for the siever. Siever finds potential relations for vector extractor. Vector extractor extract vectors for various relations and handle them to the matrix. And finally, matrix extract the solution out of the found relations in real time. Each one of the above works in its own thread. So now we are working in 4-threaded environment. And we can add multiple sievers as we wish. Until now, we didn't really use the power of parallel factoring. Now we will start to. So the solution now adds parallelism to our work. If you have any questions, please ask me in the Facebook group or comment below, and the source is going to be available in GitHub. So are you ready for it? Here we go. Okay. All the blues, it's what changed, and all the greens, it's what added. So the entire source code changed. Let me walk you through it piece by piece. We're starting with Quadratic Sieve. It goes into the solve method. So far, same thing. We defined that we want to generate some test pseudo-random 200-bit values, and we want to factor them. Then magic numbers. I created all of those classes in that singleton pattern, which just defined a final instance of the object. So those are the magic number calculations. We need probably to update those. Those are not perfect, but it's what we've been using in the last episode. So I kept them. It's just in different place. Prime base, needed to move it away as well. It just generates the primes using the same method as before. Init prime threshold. So I needed a prime base to do that. Polynomial. Now we start generating polynomials. So each one of those have new thread, and it starts running. Those are magic numbers, loops count and loop size. So m is the sieving interval. So just a multiplication of loops count times loop size. And this is the starting q value. Then we are going to the next prime q. And for each of those q's that are in quadratic residue mode, where n is at quadratic residue mode q, we are generating a polynomial. Then, instead of simply calling for the sieve, we do it like this with data queue, which defined all the queues in our system. So we have a blocking queue of polynomials data, which is polynomial data. It's just everything that we need for the polynomials, including the wheels. And it's blocked for 10 objects. So no more than 10 objects can be generated. Otherwise, the thread will block the put action. And indeed, what happens is that polynomial runs faster than the siever, and it waits. It's blocked on the put, and it just go for it just been freed, and the resources are used by other threads in the system. So this is awesome. It's not happening with executor. In the executor, it always runs. So this is a big efficiency gain in this way of working with threads. Next step, let's go back to Quadratic Sieve. So polynomial. Then we have the siever. As I mentioned, we can have multiple of those. I found that 2 gives the best performance. We start sieving. We create the logs. Max prime, loop size, and then while true, we extract the polynomial data from the polynomial data. So again, take can block until there are items available, but because a polynomial, I called it a polyminor, it works faster than the siever, then it's a guarantee that it will not block, and it runs very fast. It does what it's been doing before, is sieving using the logarithmic estimation, and generates and finds relations. So once a potential relation was found, it passed it to the vector work data. The information that it's been transferred is polynomial data local X, and C. So let's look into this queue. So it's limited by capacity of 1000. It's not reaching it because the next piece of work is the vector extraction. The vector extraction also working on its own thread and grabs the work data from the work data queue. Again, if it doesn't have items, it will be blocked and will wait for those. And the resources of this thread will be released. Later, by the way, in the future optimizations, we will see how Sieve and vector extractor are becoming our bottleneck. So meanwhile, it's not possible to create multiple vector extractors because it uses the big prime optimization and it's a singleton. So we need to find a way how to break that into to support multi-threads. But meanwhile, this code haven't been changed. It's the same optimizations that we've been doing in the last episode. And once a value was found in here, it's submitted to the bsmooth queue. And similarly, the big primes also submitted to the bsmooth queue. Final piece of the puzzle is the matrix that also works on its own thread, and it consumes the bsmooth queue, taking a value, waiting for a relation to be found, logged, and release the resources for other threads. And once it does, it adds it to the Gaussian elimination matrix, which is the continuous factorization matrix. And in here, many optimizations, two big optimizations. So the first one, let's do it slowly. We are getting a bsmooth value. We are adding it to the bsmooth list and adding it to the solution matrix. So once the solution is found, we can extract it from the bsmooth list. Next, we're iterating over the active bits of our vector and seeing and checking if we can eliminate any of those. So this portion of the code didn't change. Now we're adding an eliminator. And it can be either a solution in case its vector were fully eliminated and it's empty now, or we need to find the next bit. So in here, I change it to be the max bit. So not finding kilometers from the first bit, but from the last bit. It also saves on memory because it's easier to represent. It takes fewer bytes to represent vectors whose most highest bit that it's termed having a smaller index. We are putting it into the eliminators map. And before we had here a recursion. We don't have it anymore. It's done. And the performance of it at the worst case scenario, it's n power 2 because XOR takes O of n and the iteration over all the eliminators takes also O of n in the worst case scenario. But in the best case scenario, it's O of 1. And indeed, on average, it's much, much smaller than n power 2. So the performance of this entire algorithm rocks. Okay, so finally, the solution extraction. Before it were consuming a huge amount of memory. And now, let me show how it's been improved. So we have A. Let's start with the A because it's the easy part. A is that each relation having its own A, and we want to multiply them all together to get the final product. So A will be bismuth, get A, multiplied by A with the addition of mod n, because we know that A mod n times B mod n equals C mod n. And it doesn't matter if we multiply the AB at first or each one in that way. So we're always keeping the A at most to the size of n. Great. Now with B, we need to do more work. We are getting B that it's not a square. And what we are doing, we are dividing it by all the set bit in its vector. And then we are keeping those bits. So we have vector parts with the size of the prime base, an integer, and we are counting how many times we saw each of those vectors. Then we can take the square of next b because we know now that it's a square. So we can take the root square of it and multiply it by the b that we are collecting. B is the final product. B2, what is B2? So B2 was just for testing, right? Just debugging. So we multiply b by the square part of the next b. And we are tracking the vector parts. Finally, for each of those vectors, if it's not 0, we will take the prime, the I-index of that vector, and we will add it to the power of whatever we found divided by 2. Actually, we can do it mod power of n. Yeah, so those can as well get big. That promise that the entire multiplication will be within n. And then b equals b multiply p mod n. And this is how we are making sure that we are within the bounds of n square in the worst case within the entire process. So let's see that it still works after this last modification. Oh yeah, it still works. Cool. So this is that. And now let me show you some of the executions. Um, yeah, I added them here. So I tested running with 1, 2, 3, and 4 threads on 200 bits for episode 12, this episode. Let's close that. This showed the metrics time. Do you see that it's really in milliseconds now? Up to the end. And in the end, we are done with the new No, it's not the new record. It's 100 seconds running on a single thread. So it beats the previous record of 126 seconds, just with those optimizations and better threading between between the execution, and the overall time for the metrics, it's very small. So the solution extraction takes a second. Before it was taking like 5 seconds or 6 seconds, and the memory jumped to by 2 GB there. It was really insane. Now, optimally, it runs on 2 threads with amazing time of 64 seconds for the entire execution of 200 bits. So this is the new record. The sieve time it's inaccurate because I haven't implemented yet the support for proper logs when we are working with multiple instances of the sieve. But you can see the times of everyone else. So the polyminer, it's 54 seconds. The vector extraction, it's 46 seconds. And geometrics is just 2 seconds and a half. So all of this time of 64 seconds was most likely used by the zero. Cool. With 3 threads, we start seeing some regression. It's most likely because of my machine setup. If I had more cores, maybe it would have been working better. So this is it. We are now in a really good place of the source code, and I'm not really deleting all of all of the episode structure. What I'm going to do now in GitHub, I'm switching to work with releases and tags. So I will provide you links to the previous tag. So for each episode, you will be able to see the actual tag and the source code we've been working on that particular episode. If you have any questions, please ask me in the Facebook group or comment below. And check out all those cool changes in GitHub. See you next time. Bye.